In this video, we will demonstrate how to perform calculations using the ideal gas law. Here we have the ideal gas equation, PV equals nRT, and with it we can calculate either the pressure, the volume, the number of moles, or the temperature of any gas, knowing the other conditions. We introduce a new constant here, R, the gas constant, which has the units of liter atmospheres per Kelvin per mole. Now, it is important that all of our other variables are in these units, so everything cancels out and gives us the units that we want in the end. For example, what is the volume of 75 grams of oxygen at standard temperature and pressure? Well, there's a lot here that we haven't been told explicitly. First off, what is standard temperature? Standard temperature is defined as exactly 0 degrees Celsius. And standard pressure is exactly 1 atmosphere. Now, because the gas constant has the units of Kelvin, we need to make sure that our temperature has been converted from degrees Celsius to Kelvin. The other thing we need to know is the number of moles of oxygen. We've been given grams of oxygen. Also, we need to understand that because we're dealing with a gas, we're dealing with diatomic oxygen or molecular oxygen and not atomic oxygen. So, first off, we need to convert this mass to moles, and you need to use the proper molar mass of oxygen. You need to use the molar mass of diatomic oxygen, 32 grams per mole. With this information, we can calculate the number of moles of oxygen, and then we need to rearrange PV equals nRT and solve for volume. So once we have that new equation, we just have to plug everything in. So we have the value for moles, we have the gas constant, and we've converted 0 degrees Celsius into 273.15 Kelvin, and divide by 1 atmosphere. All of our units should cancel, leaving us with just liters. So in the end, 75 grams of oxygen at standard temperature and pressure occupies 52.5 liters. Now that's not the only thing that we can do with the ideal gas equation. For example, we can apply this to reaction stoichiometry. Calculate the volume, in liters, of chlorine gas produced if 1.5 grams of manganese oxide is allowed to completely react and cool to room temperature at an atmospheric pressure of 755 torr. Alright, so we need to know that room temperature is defined as exactly 25 degrees Celsius. We need our PV equals nRT. We're also going to have to convert that pressure in torr to atmospheres. Now, what do we need to do first? We need to know the number of moles of gas produced. We know the pressure, we know the gas constant, and we know the temperature. So all that's left is to use stoichiometry, take our 1.5 grams of manganese oxide, convert that to moles of manganese oxide, and then we look at the reaction stoichiometry and we realize this is just a 1-to-1 ratio. For every 1 mole of manganese oxide, we get 1 mole of chlorine out. So now we have our moles of gas that we can plug into our ideal gas equation. Again, we are simply solving for volume. We have our moles of gas times our gas constant. Now we need to convert our room temperature, 25 degrees, to Kelvin. And we need to use the definition of 1 atmosphere equals exactly 760 torr to convert our pressure into atmospheres. Now, check everything, make sure all the units cancel, and again, we have liters, 0.425 liters of chlorine produced. Now this is an interesting example. A lot of times in the lab, we do not measure volume, we actually measure pressure because our volumes are fixed in our glassware and our equipment. So we have a 500 milliliter flask, it's loaded with 12.5 grams of lead-2 sulfide, and it's evacuated at 298 Kelvin. Calculate the minimum pressure of oxygen that must be charged to the flask in order to completely react with the lead sulfide. Assume the volume of the solid is negligible. That's important. The volume of the solid probably does not take up very much in that 500 ml flask, so we can ignore it. Now, what does it mean by calculate the minimum pressure of oxygen? Well, right now that it's evacuated, the pressure inside is assumed to be essentially zero. We need to add enough oxygen to reach a minimum pressure in order to have just the right amount of oxygen to react stoichiometrically with that lead sulfide. So again, this is just a stoichiometry problem. Start with the mass we've been given. We're going to convert this 12.5 grams of lead sulfide to moles, and then we're going to use the reaction stoichiometry. We need 3 moles of oxygen for every 2 moles of lead sulfide. And so now we have the moles of gas that we need to charge to this flask. And from here on out, it's just an ideal gas equation. Now we solve for pressure. We plug everything in, and we need to convert our volume into liters. Very important. So now the only unit that's left is atmospheres. So we need to raise the pressure of oxygen in this flask to 3.83 atmospheres.